Okay, good morning, everyone. Okay, so welcome back after the break. Okay, so hope everybody is doing well and fine. Okay, so before the recess week, we basically completed all the hardware related aspects of the uh, new Freedom board that you learned in this module. Okay, so definitely the Freedom board is a lot more powerful than other boards that you have used, and it is capable of much more, okay, than what we have covered so far. All right, so definitely after the module is over, I would encourage you to in your free time to explore on your own, correct some of the other peripheral blocks and subsystems that are there, and how you can actually use that. All right, and you can even work on some projects on your own after this module is over. Okay, so do explore the other capabilities of this board that you have, okay, beyond what we have taught you so far. Okay, so for the second half of this module, we are going to be focusing on the OS aspect. All right, so we're going to start off with some understanding of what is OS and the idea behind OS, and how we are going to import or sort of integrate the RTX RTOS into our system and develop a complete multi-threaded code that will run our project. Okay, so let's get started. Okay, so we will be covering lecture 9 and 10 today. Both are quite short set of slides. All right, and after that, all right, so that we should be done in the first half, and then we'll take a break, and when we come back, I'll go through the tutorial for this week. Okay. For the past few batches, I've always gone through this tutorial as a whole with everybody. This is just to make sure that everybody has a clear understanding of the very basic concepts of RTOS, okay, because this is important so that you can further build upon this understanding when you learn other more in-depth concepts later on. Right, so this first lecture and this first tutorial is important to understand how, or the nature of how OS-based code works. Okay, so that is why I make it a point to run this tutorial with everybody in the lecture slot itself. All right, so let me get started. Okay, thank you. All right, so okay, let's get started with the OS overview. Okay, to get an idea of what OS is all about. All right, so when you talk about an OS or operating system, okay, there are several aspects to an OS, okay, that must be fulfilled, okay, for the whole system to be running smoothly. All right, so we are going to be talking about things like process, memory, file, okay, and I/O. Right, other aspects like network, security, and GUI are also uh, elements of an operating system-based device, okay, but we are not going to go through all of that. All right, so we're just going to get a general overview of some of the basic components that we need. Now, the first thing is an operating system, we say deals with various kind of activities, all right, and those activities are basically what we call processes. Okay, so when you launch your Microsoft Word or your Microsoft PowerPoint, or you open up a browser, all right, so that is a process that you start off. All right, so your user application, your system application, all these are processes that you can start up, and you can also have uh, multiple processes running the same program. Okay, just like how you can open up multiple Word documents, multiple browsers, all right, and so on. Okay, they can all run concurrently, and each of them are doing something different, correct? On one uh, version of your browser, you are on one web page, another browser, you are on YouTube, and so on. All right, so everything still runs, all right, because every instance of this program has its own independent memory space. Okay, so when you click on your icon to open up an application, it starts up a process. Okay, it communicates with the OS, it creates some tasks, it allocates some memory, all right, and it is able to multitask, okay, based on the way the OS operates. Okay, And all of that comes into understanding how we schedule the tasks, how different parts of a process can communicate with each other, and yet everything seems to run at the same time. Right? So if you look at your system that you deal with, whether it's your handphone or whether it is your laptop and so on, there is always this concept of concurrency. That means a lot of things are always happening at the same time. Correct? While you are uh, typing out a document, you can be playing a music video in the background. Correct? Then you can also be doing something else or downloading another file. So everything is making use of the resources of the system. Okay, and everything happens concurrently. So how is this possible? How does the OS come in? All right, so and how do you write applications that can tap on to the OS to do these kind of activities for us? All right, so that is the high level objective. Right? So the process in general is talking about the actual instance of a application that we are trying to run. So when a process is running, definitely it's going to use memory, correct? So the concept of memory is always there. So you have the program memory, you have data memory, all right? And then you also need to maybe have shared data, all right, between processes. All right, that means one process might take a data and share it with another process. Okay, so these are things we'll be talking about. All right, virtual memory. Correct. How do I tap on to secondary memory to increase the amount of space that I can use? All right, so these are also things we'll be discussing. Then many systems will also have files. Okay, so when you talk about file, of course, generally we talk about be related to the files that we have in our directories and folders and so on. But a file is just basically a collection of information, correct? So in an embedded system context, a file could be just a storage of data that you collect maybe from a sensor, okay, or from the camera, okay, and then you store it somewhere for processing later on. Okay, so like for example, you're developing a like a search and rescue robot in EPP2. You may want to have a camera where you keep on capturing your camera footage and you store it in files, okay, every hour and so on. Okay, so there must be a way in which you can access the information, retrieve it, and so on. All right, so that is file systems and IO. So IO is basically a things that you have seen before. In the first half, your input output, your serial interface, and so on. All right, so those are the kind of communication uh, framework that you have to allow your board to communicate or your system to communicate with other subsystems that you have. So the whole idea of the operating system structure is you have multiple components, okay, that may need to interact with each other, all right, and it may not be so straightforward how to organize all the components together, okay, and one of the key challenges always is you want them to be reliable, all right, you want OS to be reliable, you want it to be backwards compatible. So this is also important, correct, because an operating system that you use now, all right, may have an upgrade later on, all right, and when that happens, you also want to make sure that whatever system you have developed with an older version of the OS is still compatible, right? You do not want a case where you update your OS and then suddenly a lot of applications cannot run or they crash and things like that. Okay, then you also want it to be extensible and portable. Okay, so when you say extensible means in the future you want it to be created with a sort of structure that I can easily extend the capabilities of my code to add on more features. All right, portable again is the idea that I can port it to another hardware platform with a similar OS. Okay, just like for example, you want to be able to run it on the current hardware that your Windows system is running on. And later on, when you migrate Windows to another hardware platform, you still want it to work the same way. Correct? It must be portable to another slightly maybe different hardware configuration. Okay, but a similar OS. Okay, so that is the portability aspect of an OS. All right, so where does the RTOS come in? All right, so in a RTOS system, okay, in RTOS system, we the key word is always this, the real time. All right, that means when we say real time, we want to meet specific timing constraints. Okay, so when you talk about timing constraints or timing deadlines, all right, so there are two aspects or two sort of general categories we can put them into. One is we call them hard real time, the other is soft real time. Okay, so in hard real time, that means you want to make sure that if I have a task that is supposed to complete maybe within 2 milliseconds, it must complete within 2 milliseconds. If not, it can lead to a major system failure or a catastrophe and so on. So it's very, very critical. It has to be met on time all the time. All right. So that is what we call a hard real-time system. Whereas a soft real-time system is one where if the deadline is not worth, all right, it is fine, but it's still worth finishing the task. All right. So for example, okay, let's say you are driving a car. All right. You are driving a car and suddenly there's an obstacle in front of you, you jam the brakes. All right. So in your car, the system must recognize that when the brake is detected, okay, I must immediately activate the ABS and stop my car within a certain number of milliseconds and so on. So this whole system must kick in and respond within a specific time frame to prevent an accident from happening. Correct? So it's hard real time. Correct? Whereas a soft real time could be that you switch on the wiper, okay, or you try to change the song on your hi-fi system. Okay, and normally maybe when you press the button, you expect it to respond within maybe 1 second. If it responds in 1.5 seconds, it is still fine. Okay, so even if the deadline is not met, it is still fine, but as long as the task is completed. All right, so a hard real time means you must complete it. Okay, if not, it can lead to something really bad, okay, system failure or something worse. Okay, so a real time operating system is used in a lot of uh, application scenarios, robotics, automotive, aircraft, okay, even if we talk about now all the self-driving cars and so on. So all of them require real-time processing of information, and decisions have to be made in real time. Okay, and you need to be able to respond within the deadline. All right, if not, it will lead to something bad. Okay, so the key design requirement is always predictability and determinism. Okay, so responsiveness and user control basically is to do the right thing fast enough to make sure that you fulfill the requirements of the system. Okay, now this is a good thing to think about. When we say real time, okay, does it equal to fastest response? Okay, what do you all think? Does real time equate to fastest response? Okay, so the key thing to remember is real time is always related to your deadline. Okay, it's always related to the deadline that you have. So that means that, for example, if I have a switch, okay, and if I say that when I close this switch, the LED must light up. Okay, LED must light up. If I tell you the deadline is 1 second, so within 1 second, the LED light up is fine. Correct. If I tell you the deadline is 10 seconds, within 10 seconds, the LED light up is fine. Correct. So when I give you a deadline of 10 seconds, it doesn't mean that I have to finish it within half a second. Okay, the deadline is 10 seconds means as long as within 10 seconds I can light up the LED, then I'm still fulfilling the deadline, I'm still fulfilling the requirements of the real-time system. Okay, so it doesn't have to equate to the fastest response. You just have to make sure that you fulfill the deadline or the timing requirements of the system. Okay, so that is this important aspect you understand. And another thing is, of course, fail safety. If things go wrong, what should you do? How should you uh, sort of bring the system to a safe state? All right, so these are some things we will discuss later on towards the end of the module. Okay, on what are the implications if, let's say, you do not shut down the system properly and some real life example cases, okay, of things that can go wrong. Okay, so of course, in order for me to fulfill all these timing constraint, I need to have very advanced scheduling mechanism to switch between one task and another task, and of course all the memory that is also needed for the various tasks. Okay, so in some books or online resources, you will come across these two terms, RTOS and EOS. Okay, real-time operating systems and embedded operating systems. They are generally uh, sort of interchangeable. Okay, because most embedded systems that have an OS in them do have some form of real-time requirements. Okay, so the whole idea again, the real-time is tied to fulfilling deadlines. All right, so as long as you're able to fulfill deadlines, or you have a requirement to fulfill deadlines in order for a system to function correctly, then you need a real-time operating system in your design. Okay, so that predictability and determinism is what we are looking at. Okay, and it must be fast enough to fulfill the deadline. That's all. All right. So in a general embedded operating system, a GUI and security, these are again depends on the application context. All right. To what extent you may need a GUI, to what extent you need some security and so on. Okay, but the real-time nature or the requirement will definitely be there. Okay, so again, this comes back to the comparison between embedded real time and super loop. So again, the super loop concept was what? You have a main loop and you have interrupt service routine. All right, and the main challenge with that is you cannot always have a consistent response time. All right, because your super loop, okay, that you have, the while one loop that you have, okay, as long as I have task one, okay, task 2, task 3, and so on. Okay, uh, generally when you develop a system, there will always be changes, there will be improvement and so on. So as the timing characteristic of each task change, the time that it takes for this whole super loop will change. Correct. And when interrupts come in, the dynamics will change. When you have nested interrupts, again it adds more dynamic uh, changes to the timing characteristics. Okay, so it is never possible to accurately predict the behavior or the timing behavior of a system when you have this model. All right, unless you say it's a very simple system with just maybe one or two tasks and one interrupt and so on. Okay, so if it's a very simple system, then you can say it is quite consistent. All right, but as long as the system is evolving, there's a chance that more tasks may be added, more interrupts will be added and so on, then the timing will always change. All right. So with RTOS, the idea is instead of looking at it in terms of function, you encapsulate your functionality into tasks. All right, and then you have a scheduling mechanism. All right. So the whole idea is right now, what we're going to do is we are not going to think in terms of function A, function B, function C, or so on. We are going to think of it in terms of, let's say, task 1, task 2, and task 3. Okay, and each task will have a specific objective to fulfill. Okay, so for example, task 1 maybe is for LED control. Okay, task 2 maybe for motor control. Okay, task 3 for maybe your switch interface and so on. So you can have multiple tasks for different functionality. All right, and each of them, all right, the way we are going to be developing our architecture is each of them will run as if they own the CPU to itself. Okay, so they will run on their own, but at the same time, we know that there is always some dependency. All right, there is some communication that is required between the tasks. So LED, for example, should light up when the switch is activated. All right, but if there is no switch activated, the LED task does not need to run. It can go into sort of a sleep mode. Correct. So when the switch is activated at some point of time, I must be able to communicate that information to the LED task. Then the LED should, the correct LED should be able to light up, and then that's it. I don't need to do anything else in my LED task anymore. All right. Similarly, the motor task. All right. The motor task need not need to do anything until it receives a command from your app, for example, okay, through the serial interface. Then it should sort of activate and should start to process the information and move the motor. If there's no information, it doesn't need to do anything. All right, so we are going to be developing our architecture, okay, with this idea that I will create tasks, okay, and the each task will be written as if it owns the CPU, but at the same time, there's there are a lot of mechanisms in place to ensure that I can communicate with each other, that I can share data with each other. And of course, when you start to share data with each other, there is also a chance of data corruption happening. So we also need to look at how we can protect data, or how do we ensure that we have some mechanism in place to ensure that there is no data corruption happening because of this multitasking that is going on. Okay, so these are some of the things we'll be looking at, okay, while we are learning this course. So for this course here, I have selected this Keel RTX platform, okay. Again, this was after a lot of uh, extensive sort of digging into all the various ARM boards and all the different OS and everything. Okay, so eventually I settled down on this, and so far I think I would say it's a very good OS, and it's also a very powerful OS. And the past few batches of students have really learned a lot, okay, using this OS to develop. All right, the other alternative, of course, that you can try on your own after all this over is the Embed OS, which I showed you in the, I think, the first lecture on how to use the Embed OS platform, okay, and how to run your code on that. Okay, but for our module, we'll be using the RTX. Okay, so in this week's lab, you're going to be sort of loading your first OS based code onto the board, right? And you're going to see this in action. Okay, and we also are going to be leveraging some of the CMSIS APIs. All right, so the CMSIS RTOS API is another sort of layer of library calls for the OS functionality, but we are not going to use all of it. So it's going to be a mix of the Keel RTX lower level kernel with some of this CMSIS library calls. All right, so when we are looking at the code and the lab, you will see how these two link together. All right, so that is the RTOS for this course that we are going to be using. Okay, so let's go on to the next chapter on processors. Okay, so this chapter on processors is to give us a bit more better understanding on how processors are created and how this multi-threading concept actually is managed by the OS. All right, so this is again a very important concept, because if you understand this process management well, then when we look at the other aspects of the data sharing and communication and so on, you'll be able to better understand that. Okay, so we're going to look at memory processors, how it works, okay, how do we switch between different processors, and then we're going to go through some RTX example code. All right, and with that, we're going to focus on this context switching and the states. All right, and once we do that, we can actually take this understanding and look at the tutorial and the lab as well. Okay, so this is what I mentioned just now. When you say you create a process, it is actually a process which is an instance of a running program. All right, so if you launch your Keel IDE or you launch your browser or anything, you can have multiple sort of copies of it running. Okay, and each of it has its own memory space. All right, so you can be doing different things in each of these instances of this process. Correct. So that is basically the whole idea of OS as well. You can create multiple tasks, and multiple tasks can actually be doing similar things as well. All right, but of course, when you write your code, you have to be aware of what other tasks are using, and whether if you are dealing with a shared resource, how do you deal with the shared resource. Okay, so take for example right now. Okay, right now, like for me, I'm using my PC, so I'm using the screen. All right, but at the same time, I also have my web browser that is open. Correct, my Microsoft Word document that is open. All right, but all of these processes, the web browser, the Microsoft Word, the PowerPoint, all of them have the ability to use my computer screen, correct? But only the PowerPoint is using the computer screen. The others have been blocked from using the computer screen, correct? So that is the example of having different processes, all with similar ability to use the screen, but at any point of time, only one of them can use the screen. So I need to be able to enforce that. Okay, so similarly, when you write your code, you may have different tasks that may control the LED, different tasks that may control the motor. All right, but you should be aware of this, and you should make sure that if one task is controlling the motor, I should not allow another task to come in unless that is also part of the design. Correct? That means if, for example, I want to be able to create a split screen where one side is PowerPoint, the other side is Word at the same time. Okay, then that is a different objective. All right, if I only want one screen or the screen to be only used by one application at a time, then that should be the way you design the system. Okay, so how you want to share resources with different tasks. Okay, all these are your own design choices. Okay, so some maybe design methodology that you have, you may allow different resources to be shared. Some cases you may want it to be exclusive. Okay, if one task is using, the other task should not be able to use, and so on. Okay, so these are things that we will learn how to use or how to code with the RTX, okay, on our board. Okay, so when you create multiple processes or multiple tasks, okay, so one thing I want to say first is this term process and task is again used quite interchangeably in many references. Okay, so sometimes they call it multitasking, sometimes they call it multi-threading, okay, sometimes they call it multi-processing, and so on. All right, all of them have the similar idea. Okay, in some books they like to call process as a higher level process and task as sub processes within the main process. Okay, take for example, okay, for example, you launch a web browser, okay, and I say that this is a process. Okay, I call this a process. So for this process to run, what do I need? I need to have a task that can do network, correct? Because I need to send and receive data packets through the network. Then I also need a task to interface with my IO, correct? Then I may also need a task to communicate with my screen. Okay, so yeah, input output screen and so on. Okay, so you may have a different task for different uh, activities that your process aims to carry out. So some books like to reference it this way. For me, I generally say that they are all interchangeable. That means you can also look at this as a task, and one task can spawn multiple tasks after that also. All right. So it's just terminology. All right. So in our notes, all right, I use task or process interchangeably. So either way, it refers to the same thing. That means it refers to an instance where I have created a task or a process that is going to run some activity, and that task can also create other tasks if I want to. Okay. So when I create a task, okay, when I create a process, the operating system will give me some of this information, or set aside some of this information inside what we call a control block. Okay, TCB or PCB. So what is this control block? This control block maintains a record, okay, of all the information that is related to the process. That means what is the ID of the process. Okay, so when you create a new process, the OS gives us an ID. All right, this is for the OS to keep track which task are we referring to, correct? And since the task can be in different states, okay, which we will cover in a while, I also need to keep track of the state of my task. Okay, and at the same time, like what I mentioned just now, each task is going to be running as if it owns the CPU to itself. That means the task will have its own copy of the program counter, the stack pointer, all the registers that it's using. Okay, so it has its own copy of it because it is running sort of on its own. Okay, so all of this information is there, plus the scheduling information, the memory, and all this other stuff. Okay, interprocess communication and all this. So it basically gives us a complete record of everything related to the process at any point of time. Okay, and why is this important? Because in a multitasking context, okay, when I have multiple tasks running, in order to allow these multiple tasks to still run concurrently, there is this idea of switching that is happening all the time. Okay, so in the background, you will always have tasks that are switching from one to another and so on. All right, and this multitasking, okay, is actually all these tasks switching around very, very fast that give us the idea that everything is happening at the same time. Okay, but actually only one thing is happening at a time, but everything is happening so fast that is giving us the impression that it is happening concurrently. All right, so because of this constant switching around, okay, there is the need to make sure that I capture all this information related to a task accurately and correctly before I switch over to another task. Okay, so that is why we need this task control block. So a process while it is running, you will have the CPU time, okay, a portion of the CPU time that you will actually use to execute. You will have memory for it to run its code, plus the ID associated with it, plus all the tasks that we create. Okay, so the idea, like I said, is it creates an illusion, okay, that it can run by itself, okay, because it can have the full CPU to itself at that point of time. Okay, so it has its own dedicated memory, its own copy of the program counter that registers everything. But at the same time, okay, we also know that we have the ability to allow inter-process communication. So one task can talk to another task, all right, to share information, to sort of synchronize and so on. So these are also things we will look at. Okay, this is the memory layout of a program. All right, in a later chapter, we will go through this in more detail. Okay, but for now, we can just have a high level view that the code will occupy some part of the memory. All right, so these are basically the instructions to be executed. Okay, the binary instructions, and we use the program counter to point to this memory space because that is where the instructions are being stored. Okay, and of course, when with every program, you also have data, so you need memory to store that. So you have static data for your global variables, static variables, and so on. Then you also have your heap and stack. So heap is when you want to use malloc, and stack is for all your procedural calls and your stack pointers and so on. Okay, so again, you will go through this memory aspect in more detail later on. But for now, we can see that every instance of a program or a process requires some memory space. Okay, so we need that memory space as well. So when we create a process, okay, we need to make sure that we are able to have all the resources that the process needs. Okay, which means that when I switch between one task and another task, I need to keep track of all of this information accurately. Okay, so I need to keep track of all the memory that it was using. What code was it executing? What was the stack pointer value? How much of the heap it used? What are the global variables? All this associated with that particular task. All right. What are all the register values? Okay, and of course the OS state as well. Okay, so all of this information needs to be captured. Okay, all of this is captured and stored, okay, in a way that when I am going to switch from one task to another task, all right, I'm able to switch over, and when I'm coming back, I know exactly where I left off. So the idea is quite simple, I mean quite similar to the idea of the main loop and the ISR. Okay, so if you go back to our very simple main loop and ISR, okay, we say that since the ISR can happen anytime, when the ISR is detected by when the interrupt is detected by the system, and before I jump to the ISR, I need to be able to save my context. That means whatever registers that it was currently using for the execution of the instruction at the time, the program counter value and so on. And then I jump to the ISR. When I finish, I must be able to return back. Okay, so in a single threaded context, it is easy because you only talk about the registers plus the program counter, and so on. Okay, so it's just a small amount of information. Okay, but the same thing now you amplify it, because a process is like a whole system by itself. Okay, so you have a lot more information to store before I can switch over to the next process. Okay, and then I can carry on, and I must be able to come back and resume from where I left off. Okay, so that is where you need to make sure you have the ability to store all this information, and that is where the task control block comes in. Okay, so this task control block, okay, that is automatically created for us when the task is created, has all this information already preset for us, and is updated as you are executing your program. Okay, so again, do not be overly concerned with all of this first. Okay, we don't need to look into all of this in detail, but for now what we need to know is the task control block gives us this information on your stack uh, memory, where you're pointing to your program counter, your registers, your priority level, your task state, and so on. All right, so these are all the information that you need, so that when you want to come back to this task, you know how to resume from exactly where you left off. Okay, so now let's look at the process creation. So when you create a process, okay, that means when you start a new task or a new process, the OS will give us a unique ID. Okay, so that will be used by the OS to reference this process or this task. At the same time, it will allocate memory, okay, for the process control block. Okay, so to store all this information, you need some memory. All right, so you will have to allocate some memory for the process control block, okay, and other control structures, okay, and the user memory. So whatever memory you need for your code, we will also allocate for you inside, okay, once you start a new task. Okay, and then you will initialize this task control block, all right, and then you will link the task control block, okay, with the scheduler. Okay, that one later we will look at it. How about terminating a process? Okay, so termination of a process is similar to, for example, you open up your web browser, and when you're done, you click on the cross. So when you click on the cross, you terminate the process. Okay, so when you terminate the process, what are you doing? You are basically releasing the resources, okay, so that the resources, the memory is freed up, and the OS can now use those resources for another process, and so on. Okay, so that is for general purpose OS systems. In embedded systems, generally we say the processes may never terminate. Okay, so you look at it later, okay, when we're writing the code, we will generally write processes or tasks such that they never terminate. It's just that whether I need to do anything now, or I'm just waiting for some trigger, okay, some event to happen, and then I start processing and start running my code. Okay, so we never write it to terminate. Okay, because if you terminate, then you say that you don't need this task anymore at all right? But in an embedded system context, it's not like your PC, right, where anytime you want, you just move your mouse and then you double click and you open up the process again. Okay, so in an embedded system, when the system start up, all the tasks should also start up, okay, generally, but not all the tasks may be running at that time. Okay, so when as and when the event is triggered, some data comes in, then you start to process the information, so the task sort of wakes up and starts to process it. Okay, but once the processing is done, there's no new information, it goes back to sort of a waiting state. Okay, so let's look at that in a while when we look at the process state. Okay, so this is what I mentioned just now about the context switching. So when process A is running, okay, it is updating its process control block with all the necessary information, all right, relating to its current state of execution. Okay, and let's just say that at some point of time, process B is now scheduled to run. Okay, so when process B is scheduled to run, before I can do that, I need to save the process control block of task A and load the process control block of task B. Okay, so the process control block again contains all this necessary information, the registers, the program counter, the memory, the OS state, and so on. Okay, so once I save the current context and I restore the context of process B, I can now start executing process B. Okay, and at some point of time, again, once I, for some reason, decide to do a context switch back, so I need to again save the context of process B and restore the context of process A. Okay, so as you can see, it does take some time. Okay, it does take some time, certain number of clock cycles. All right, but all of this we do not factor in too much because we say that this is again running in the background. So in the background, your OS helps to do all this stuff for us. All right, so our focus is not to worry about the context switching. We are focused on writing the task to fulfill the requirements of the system. Let the OS handle this heavy lifting at the background for us. Okay, we focus on the front end application. Okay, what do we want our OS system to do for us? All right, so that brings us to the process states. Okay, so these process states are the okay. So there's a question: what does it mean to save state to PCB? So when you say save the state to PCB, okay, that means you are, because while you are running, okay, you are currently okay. So like I said, when any task is running, the task makes use of the CPU's resources to execute. Okay, so while it is running, it is making use of the current set of registers, the program counter, and so on. All right, and that is the current state of the CPU. I mean, current state of the process. So when I say I want to save this state, that means since this state that I'm currently running, so when I'm executing at this point of time, the state that I'm representing is that of task A. So when I'm going to switch out of task A, I need to save all this information to the process control block of task A. So process control block of task A is the one that holds a snapshot of the current state of where it was executing before a context switch happens. Okay, so when I switch over to task B process control block holds the state of where it stopped last. Okay, so when I load from task B or restore from task B process control block, I can restore the exact point from where I left off and then carry on from there. So that is what the save and restore is for. Okay, so for process states, okay, so for process states, whenever we create a new process or a new task, we say that it can occupy one of these 5 states. Okay, you can occupy one of these 5 states. Now, let's understand this state transition diagram. Okay, this state transition diagram is critical for us to know exactly how the system will behave. All right, so the first thing, all right, is new. Whenever I create a new task, okay, later we will see the example. What will happen is the OS will automatically admit that process into what we call the ready queue. Okay, so inside this ready state, there is what we call a ready queue. Okay, so for example, I create 3 tasks: task 1, task 2, task 3. Okay, so task 1, task 2, task 3 all will join the ready queue. Okay, and when they join the ready queue, okay, what will happen is the OS, okay, has a sort of a manager which we call the scheduler. Okay, and the job of the scheduler is to look at this queue and decide of this queue is definitely what happens is in the background this queue is automatically rearranged based on priority. Okay, so when you have multiple tasks that are in the ready queue, the one with the highest priority will always take the top of the queue. Okay, so that is the nature of a real-time operating system. The highest priority queue would always a highest priority task will always take the top of the queue. So when, okay, so for example, in this case, task 1 is highest priority. So the scheduler will automatically take the task which is in the front of the queue, all right, and dispatch that task to go into the running state. Okay, so that is what this dispatch is. It scheduler assigns CPU to the process. So currently, once you transition from the ready state to the running state, that means you are actually executing your code. Okay, that means you are running your code. When you're in the ready state, you're not running your code yet. You are still waiting for your chance to run. Okay, only when the scheduler selects your task and you transition to the running state, then you are actually executing your code. Okay, so once you're executing your code, all right, a few things can happen. All right, one is you can sort of have a timeout, okay, or you can sort of voluntarily give up the CPU if you want, and then you switch back to ready state. That is one possible option. The other possible option or possible scenario that can happen is while you are running, you want something and you cannot get it. Okay, and you cannot run without that, for example. Okay, so you go to a block state. Okay, so what do I mean by that? So for example, you are running an application that must play some music. Okay, that means you need access to the audio system of your device. All right, but currently your audio system is used by some other process. Okay, maybe you're playing some other music with another application, and since you cannot carry on anymore, all right, because you can only run, okay, if you are able to get access to the audio system. So if you cannot get access to audio system, I cannot run, so I will go to a block state. That means I need to wait until the audio resource is released, okay, and I'm able to acquire it. Okay, so that is what we call a block state. So a block state means you want something but you cannot get it, and since I cannot carry on without what I want, I have to block. Okay, so when I block, what happens? So when I block, I will free up the CPU, correct? Because when you are running, you are using the CPU. So when I go to block state, I am not using the CPU, which means that the scheduler can now come in and select another task to come and take over the CPU. Correct. So if let's say task 2 is medium priority and this is low priority, then task 2 can be scheduled to run. Okay, so originally task 1 was here, and then from task 1 it goes to the block state, so task 2 can come here, and then task 3 is still in the ready state, and so on. Okay, so that is the kind of transitioning that we are looking at, all right, between states depending on how your code is written. Okay, so when it comes to multi-threading code, a lot depends on how you write your code, how you decide to allocate resources, when you run, when you choose to wait, and so on. Okay, so if your code structure itself is not written correctly, you may end up in a situation where you are not really allocating the time required for all the tasks to run. Okay, so later, okay, when we're looking at the tutorial and the demo, I will show you what I mean. Okay, so the way we structure our code, the way we make use of the OS calls is important. All right, so I will talk more about this later in the tutorial example. Okay, and so just to finish up this slide, so if currently task 1 is blocked, okay, when task 1 is blocked, okay, because it is waiting for this audio resource, correct, it needs access to this audio hardware. And finally, okay, maybe the audio was used because you were running the Windows Media Player or something, and you closed that Windows Media Player. Okay, so since you closed that application, the audio resource is free, and now task 1 is able to acquire that. All right, so when task 1 is able to acquire that, then it will become unblocked. Okay, so when it becomes unblocked, all right, then it will transition. So you can see here, there is never an arrow from block to running. There is never an arrow from block to running because only the scheduler has the power to authorize who can run. A task cannot decide by itself that it wants to run. Okay, a task can only change, the OS can only change the state of a task to tell the scheduler whether it has the resources to run or not. Okay, so the state of the task already tells the scheduler whether it can be dispatched or it cannot be dispatched. All right, so once the resource is available, the task will transition to the ready state. So task one will come here, and then the scheduler will allow task one to run. Okay, so what will happen? Okay, in this kind of scenario, I will come back to this in the tutorial example. Okay, but I think what is important here is to understand that when we are developing our code, we must develop it in this mindset that the tasks are written to perform specific actions, but whether that code is executed or not depends on how we develop the whole architecture. All right, so that whole architecture plays a significant part in how the system is going to behave. Okay, and what the last one is this exit uh, state. Okay, again, we do not talk about exit because we will write all our tasks as tasks that will run forever. So we'll never exit. So as long as the system powers up, the tasks will be created and then we can run them according to how we have designed the system. Okay, so the process state, okay, like what I mentioned just now, is critical because that state information is what is used by the scheduler to decide who should transition to the next running state. Okay, so inside the OS, okay, there is a RT list that actually maintains this list of processors on who should run. Okay, so you can look at that if you're interested. Okay, so that gives you some internals of how the OS works. All right, but again, we are not going to go into the internals of the OS. We are looking at more of the application aspect of it. Okay, and these are some of the states in which you can or the task or the state task can be in. All right, so we will be looking at this in some of the examples, okay, in the future labs as well. Okay, so that brings us to the end of the lecture slides. Okay, so again, the key idea is to give you an idea of how OS code is developed. Okay, how it functions at a very basic level in terms of state transition. All right, and then when we look at the tutorial questions, we'll be able to sort of have an idea how it works. Okay, so before we go for a break, just a few things. The project, I think before the recess week, you are supposed to collect your chassis kit. Okay, so if you have not done it, please do it. Okay, another thing is the chassis kit and all the hardware is for you to keep. Okay, so you are allowed to customize and do whatever you want with it. Okay, so we are not going to collect it back, so you can decide and do whatever you want with it. If you want to do 3D printing, you want to do any other add-on and stuff like that, it's all up to you. Okay, so you can customize it whichever you like. Okay, the lab demo is due next Friday. Okay, as I sent an announcement also to remind you all. If you're already done and you want to present this Friday, it's also fine. Okay, so you either do it this Friday or you do it next Friday. Okay, to just demonstrate the functionality that you have an app that you can control the LED, you can control the motor. That's all. That's all you need to show. Okay, you don't need to go do any code review or explain any hardware. You just demonstrate that you already can do this functionality. Okay, so we will take a break now, 10 minutes break. Okay, so you can also look through the tutorial questions quickly, all right, and look at the state transition diagram and try to relate back to what we just discussed and see if you are able to answer those questions. Okay, so in 10 minutes time we come back, we will review the tutorial questions, and those tutorial questions, the later half of them are also directly applicable to the lab. Okay, so it will also help you in this week's lab as well. Okay, so we will take a break now and I will see you back here in 10 minutes time. Okay, thank you. Okay, so welcome back. So I've just sent you all a link in the chat. All right. So that link is to the Kiel online documentation. All right. So for this RTOS that we're using, the RTX 5, this online documentation is very handy and very useful. So you should always keep this with you. I will send it as an announcement also later. Okay. So if you look at this, let me share screen. All right. So this will bring you to this page here. So we will be referencing this online documentation quite regularly, all right, for the rest of this second half of the module, all right, and of course, I will also extract out some of the information in our slides and so on, all right. But if you always want to read up more, you can come back to this slide here, okay, to read and understand things a bit better, okay. So let's start off first with the tutorial, okay, and then I will come back to this uh, web page here when we need to look at the actual code. Okay, so let's uh, look at the tutorial for solutions. Okay, so the first few questions is on the state transition diagram, all right, and the whole idea of this tutorial is to make sure you have this concept, the foundation on multi-threading clearly, all right, and at the same time, it also gives you the necessary sort of understanding you need, all right, for this week's lab exercise, all right, when you start off building your own multi-threaded code. Okay, so this is basically the state transition diagram that we just saw, all right, where we have the different states, all right, and the transitioning between the different states as for the task. Now let's look at the first scenario here. So in this scenario, we are told that task A is running and it chooses to give up the CPU voluntarily. What state does it go to? Okay, so I have a task A that is running. That means I already created the task. Okay, so when I create the task, it first comes here. Task A first comes here. And after, since, okay, assuming there's no other task, your scheduler will select task A to transition to the running state. So task A will come here. Now, after it runs for a while, it chooses to give up the CPU voluntarily. All right. So which state will it go to? So there's only uh, two states here, correct? I mean, we don't consider exit, like I said, because all our tasks are written to be in a forever loop. All right. So they will always be running. So it's either you go back to ready state or go back to block state. All right. So which state will it go to? Okay, so some say ready, some say blocked. Okay, now so this comes back to what I mentioned just now. All right, so when you are running, you will transition to this block state. Okay, only when you want something. Okay, you want a resource and you're not able to get it. Okay, when you want a resource and you're not able to get it, then you transition to a block state. That means you cannot carry on running. Okay, you need that resource. Okay, and you're not able to get it. But in this case, I am running and there is no mention of any resource. Right? Okay, because I voluntarily give up the CPU. Okay, that means I am running and I can actually carry on running, but I choose to give up the CPU. All right, that means when my turn comes again, I am still having all the resources that I need to run. All right. So in a situation where I give up the CPU voluntarily, I will transition to the ready state. Okay. So the block state is when you want something and you cannot get it. Okay. Then you transition to that state. All right. In this case, you are having all the resources you need, but you still choose to give up the CPU. So you go to the ready state. Okay, so task A will go to the ready state in this situation here. Okay, so along the way, if you have questions, please feel free to ask me. Okay, I'll put in the chat. Okay, so far, any questions about this? Okay, so let me go on to the next BO here. So task A is running. Okay, so we are carrying on from where we left off. So now task A is here and task B becomes ready. Okay, and task B is a higher priority task. So what will happen? So let's look at what we understand so far. So just now I mentioned that the decision making body is basically this person called the scheduler. Okay, the scheduler is the person or the sort of entity in charge of deciding from the ready queue who will be selected to transition to the run state. Okay, so currently task A is running and a higher priority task B comes in. So what will happen? Okay, so task B, since it is higher priority, all right, the scheduler will automatically transition task B over to the run state. Okay, so task B will now run. Okay, task B will now take over the CPU and start to run. Okay, so that part we should be clear, right? Because the highest priority task will always take over the CPU. So since task B is higher priority than task A, task B will now transition from ready to run. So now the next question we need to answer is what will happen to task A? Will we say it goes to the block state or will it go to the ready state? Okay, so I see some answers coming in. All right, so again, it comes back to what I said just now. Task A was running, but now it cannot run. Why it cannot run? Is it because it was not able to get a resource? No, correct? It cannot run not because of any resource issue. It cannot run simply because somebody more important came along. Okay, so somebody more important, a higher priority task came along. So that is the reason why it cannot use the CPU anymore. So when that situation happens, task A will transition back to the ready state. Okay, so you always have to look at what happened to cause this task to perform a context switch. Okay, so a context switch is basically what we're talking about, right? That means you're switching from one state to another state. So task B is switching from the ready state to the running state. So task A has to switch out from the running state. Okay, but it is switching out of the running state because somebody else, some other task of higher priority came along. So it still is able to carry on running, correct? If task B was not in the picture, task A would still be able to carry on running, okay? Because it was never a resource issue. It was just that higher priority task came along. So because of that, it has to transition to the ready state. That means it has to join the queue and wait for its turn, then it can run. Okay, so that is why task B will go to running and task A will go to ready. Okay, so there's a question here. Okay, so this question I'll answer later because it is following up later, okay, on what happens later on. Okay, so let me keep that question on hold first. Okay, so now task B is running and task A is here in the ready state, correct? So after some time, task B requests for some resource and is unable to acquire it and is unable to proceed without this resource. What happens? So task B, where will it go to? So this one should be quite clear already, correct? Because I've been saying this a few times. The moment you want a resource and you cannot get the resource, you will go to block state. So task B, okay, task B will go to the block state. Okay, so once task B goes to the block state, what happens? There is nobody using the CPU. Correct? So if nobody using the CPU, again the scheduler will come in and look at the ready queue. So who is in the ready queue? So task A is in the ready queue. So task A will now transition and take over the CPU. Okay, so that is what will happen over here. Task B will go to the block state and task A will go to the running state. Okay. Now, currently what is happening? Task B is here blocked because it's waiting for a resource, and task A is in the running state. Now, after 5 milliseconds, the resource required by task B is now available. So what happens? So where will task B go to? Okay. Okay, so I see some of your answers. Okay, so good. All right. So what will happen is, first step, we can see that there is no arrow, like what I mentioned, no arrow from block to running. Okay, so no task can decide by itself that it wants to run. It all comes back to the scheduler over here. Okay, the scheduler will decide. The only thing that we know is once the resource becomes available, okay, the task will be allocated the resource and it will automatically get unblocked. So it will transition to the ready queue. All right. And assuming that there is no other task, all right, that means only task A and task B in the system. Task A is running and now task B is ready. And since task B is higher priority, task B will now transition to the running state. Okay, and task A was running, but since the higher priority task came in, task A will now come here to the ready queue. Okay, so there is no timeout here. Okay, there is no timeout here. You are basically running until you decide to give up the CPU or you go to a block state. Okay, so that is what I mentioned just now in the lecture slide. The way you design your task is very important because if you have a high priority task, okay, so for example, in this scenario here, okay, task B is running, and the way you write your code for task B is such that it just hogs the CPU and never allows any other task to run, then task A may never get a chance to run. Okay, so when you are dealing with different priority tasks, you must take into account how they are actually going to transition from one state to another state. Okay, so the design of your code, the architecture is important. So in this scenario, if task B is higher priority than task A and task B never gets blocked, never gives up the CPU, then task A will never get a chance to run. Okay, so that would be a not so good design of your architecture. All right, that means when you design an OS based code, you must design it with the mindset that all the different tasks or different priorities should be able to run when they are needed. So you should put in the mechanisms in place to allow this context switching to happen. Okay, how it can happen is what we will be learning in the next few lectures. All right, how we can put in some mechanism to synchronize tasks, to pass data around, and make sure that task A also get a chance to run and things like that. Okay, so for this, okay, task B will go to ready state, okay, and then it will transition to running state, and task A will go to the switch from the running to the ready state. Okay, that is the state transition diagram. Okay, so let's look at your code base now. All right, so this is basically from your what you're going to be doing for the lab manual. Okay, so for the lab manual, the first part of it, you're going to be looking at creating your own OS based code. Okay, so let me just bring it up here. Okay, so for this week's lab, okay, you are required to create a new RTX project. Okay, so I given you all the steps, okay, how to do it. All right, so you need to first make sure you download the support legacy pack from this, okay, from this link over here, and then you should be able to see all these files, and then you follow these steps to create the new RTX project. All right, so you need to make sure you select RTOS2 kill RTX 5, okay, that library to be included. Okay, and once you create your project, you will see something like this. Okay, and then this will be the first starting point that you will get to see. All right, which is what we are discussing now in today's tutorial. Okay, so give me a minute. Okay, so another thing is, before we carry on, there was another document that I just uploaded on called challenges with the RTX. Okay, so what we found last semester is some of the students somehow install a different version of the kill software or something like that, and it caused some issues. All right, so in that document that I just uploaded, is inside the lab folder, okay, for our module. If you trying to run and you have issues with the compiling and so on, please refer to the document and check the settings to make sure you're using the correct version of the kill software and the RTX library. All right, usually that help to resolve the issues that the last batch of students saw. Okay, now for this, once you create your RTX project, by default you will get this. Okay, so let's explore this in detail to understand what is happening. Okay, so as you can see, what is happening here is this system call clock update we have been seeing all the while. All right, that one is nothing new. All right, and then we have to call this library function called os kernel initialize. All right, so this kernel initialize function is to set up all the low level sort of support needed for the OS. In terms of the hardware blocks, the timer blocks, the kernel, all the resources it needs, the memory, and so on. So all the initialization, loading out of the OS, everything is done through the OS kernel initialize. So that function sets up everything for us. All right. So that is the first thing we need to do. All right, and then when you want to create a new task or a new thread, we have to call this function called osThreadNew. Okay, so osThreadNew takes in 3 parameters. Okay, one is a name here, add main, then null and null. Okay, so this is where the online documentation will be very useful. So if you come back to this website here, okay, under thread management, okay, you can go down and check for osThreadNew. Okay, so the detailed documentation and all the explanation is given for all the OS kernel calls that you'll be using. Okay, so you can always refer to this document, this online resource, if you want to learn more. Okay, so what I have done here is I have extracted out the main information, okay, which basically tells us that the 3 parameters that we pass in is, one is the actual thread function. Okay, in this case, it is add main, which is this thread function here. The second is any argument. So when I create a new thread, you can also pass in arguments, okay, or parameters into this function, into this thread that you're creating. And the last one is attributes. So these attributes, we will actually be looking at it in the next lab. But attributes refers to things like the memory, the priority level, and so on. Okay, so if you want to create a thread with different priorities or different sort of settings and so on, that is where the attributes field comes in. Okay, but for now, we are creating a thread with no arguments. Okay, we're not passing in any arguments, and at the same time, we're not changing any of the attributes. The default values are what we are using. Okay, so those are the 3 parameters that we are going to call whenever we use this kernel called osThreadNew. Now, the next thing, when will add main be called? Okay, so I say that I'm creating a new task or a new thread called add main, but where is it called? All right, so you can see that inside the main, there is no call to add main. All right, I never explicitly called add main. All right, because add main is not a normal function. It is a thread or a task that you are creating inside the new multitasking environment. All right, so this is a very important concept to understand. So it is not like a function call. So in a normal function call, if I say add main, okay, and I have it inside my main here. Okay, that means when I call add main, I will jump to the function called add main. Okay, finish it, and I'll come back here. Correct, but that is not what we are having here. Okay, in our scenario here, add main is not a normal function. Okay, add main is a thread. Okay, it's a thread that we have created. So after we create the thread, okay, after we call os kernel initialize, we can call os kernel start. This os kernel start starts up the multi-threaded environment. So until this point, that means until this point here, before I call os kernel start, I am still operating in single threaded mode. Okay, that means I'm still executing sequentially line by line and so on. Okay, it is what we are doing all the while, or we have been doing all the while. But the moment I call os kernel start, I am switching from single threaded mode to multi-threaded mode. Okay, that means the multitasking now takes over. Okay, so once that happens, it comes back to our state transition diagram we saw earlier. That means you can now have multiple tasks that have already been created and that are now in the ready queue. Okay, and the scheduler will come in and will select the highest priority task to run. Okay, so in this scenario, I have not created any other tasks. Okay, and admin is the only task in the system. So once the OS kernel start is executed, I will immediately start to run admin. Okay, and again, you can see that inside the admin, I have a infinite loop. Okay, and all our code is, all our tasks are created with this concept in mind that they will run infinitely. All right, but of course, there will be mechanisms put in place to ensure that other tasks also get a chance to run. Okay. So why is there a need for the for loop in the admin? Okay, so this is what I just explained. Because in embedded OS context, we say that the task should run indefinitely. All right, should run indefinitely. So we put everything inside a for loop. Okay, but we will put mechanism in place for it to transition between one task and another task. Okay, so this to remind me that I actually have a poll for this. Okay, so I launched a poll now. Okay, so in the poll question, I'm asking you what happens when you remove the for loop in the main. That means I'm talking about this for loop here. Not in the app main, I'm talking about the main function. Okay, so the task, app main is a task. So we know that the task is you need the for loop because in an embedded OS context, everything runs indefinitely. All right, but in the main, after I call OS kernel start, there is still another for loop there. All right, again, this is the default code that is generated the moment we start the project. All right, so what will happen if I remove that for loop? Okay, so let me share the results. Okay, so the majority of you say that the code will execute add main only once and then will terminate. Okay, interesting. Okay, this I will later when I'm doing the demo, just remind me to demonstrate what happens. Okay, I don't want to tell you what happens. I will demonstrate and show you. Okay, so later when I switch over, you just remind me that I need to demonstrate this. Okay, but again, understand that we are talking about this loop here. That means the loop that is after the OS kernel start. All right, this for loop we know the reason. Correct, is because of the idea that all the tasks should always be running indefinitely. Okay, but the other for loop, what will happen if I remove this? Okay, so I will not tell you anything now. Later, I will demonstrate. Okay, when we are switching over. Okay, now let's look at this code over here. This is the uh, code that you are expected to write, okay, for your lab. Okay, so it's leveraging on whatever that you've done before. So the LED control functions are things that you've done before, init GPIO or RGB. Okay, so these are your own library code that you have to put in, correct, that you've been using in the earlier labs. The only thing that is different is previously you call it in your own functions. Now you're going to call it in a task called admin. Okay, so inside this admin, what is going to happen? I create this new task admin. Okay, and inside admin, I have LED control on and off, and between that, I call OS delay. Okay, so when we call OS delay, okay, when you call OS delay over here, what happens? So again, the best way to always figure out what is happening is to go back to our documentation. Okay, so if you look under your OS delay, it says that the OS delay waits for a time period specified in kernel ticks. All right, so this OS delay allows us to wait for a certain number of time, and the important thing is the delayed thread is put into a block state and context switch occurs immediately. Okay, and once the amount of ticks has elapsed, I will transition back from the block state to the ready state. Okay, so what will happen? That means over here, uh, so over here what will happen is I will on for 1000 ticks. Okay, so once I switch on, I will delay for 1000 ticks, and then I'll switch off and I'll delay for another 1000 ticks. All right, so by default, the system, the configuration is such that one tick is 1 millisecond. So 1000 ticks is equivalent to 1000 milliseconds, which is 1 second. All right, so that is what you will observe. Okay, so let me show you that in the code. So that is what I have here. I have the LED red thread created. Okay, and here I will call OS delay 1000 and again OS delay 1000 here. Okay, so let me build it. Okay, so let me bring up my camera. Okay, so now if I run my code, okay, you will see that the red LED blinks for 1 second on, 1 second off. All right. So what is happening is over here, I'm forever stuck in this loop. All right, this is a forever loop, so I'm always stuck here. And I on the LED, OS delay for 1 second, off LED, OS delay for 1 second. Okay, so this part, I think we can understand, we can relate to it. Okay, so this is the next question. What will the CPU execute during that delay time? Okay, so when I call OS delay, I know that I put my task in a block state, correct? There's not a documentation state that I will put my task in a block state. And then there is no other task also, correct? I only have created one task admin and there's no other task. So what will I be actually executing during that time? Or what will the CPU be doing at that time? Since I have no other task to execute.
Some other task.
Like example, because we don't have any other task that we have created, correct? We have only created. Okay, so CPU just chilling. Okay, yeah. So it is sort of chilling. Okay, but what is it actually doing? Okay, so let me show you. So if you come back to our code that is currently running, okay, and if I were to stop the code, okay, you can see down here that there is actually a RTX. Okay, so it is a bit small, but you can see there is the RTX timer thread, there is the RTX idle thread. Okay, that is still running in parallel with my LED red thread. This LED red thread, okay, if you look at the bottom right hand corner, that is what we have created. Okay, but what is happening is in the background as part of the RTX to keep track of the timing and all this context switching and so on. There is a timer thread that is also running. Okay, and there's also an idle thread that is running. Okay, so all of these are related to uh, keeping track of the OS and the activities that it needs to monitor. Okay, so there will always be some background activities or background tasks that are run, but these are transparent to us. Okay, they're not shown to us. Okay, because we focus on the application aspect. Okay, what we want the OS to do for us. All right, so that gives you the idea of what is happening in the background of the system. Now, what if we use a normal delay? Okay. Now, that means right now we say that OS delay is a delay where we are tapping onto the OS kernel, correct? Where we say that we are changing the state of the task from running to block. Okay. And that will allow other tasks to run. Okay. But if I were to change it, okay, to a normal delay, what will happen? It will still have a similar sort of behavior, but the important thing is in OS delay context, we are freeing up the CPU. If I use normal delay, like what you've been using in the earlier labs and so on, you are still executing code. In OS delay, you're not executing code. You are actually blocking this task and allowing another task to take over the CPU. Okay, if I replace it with a normal delay, you are actually executing code, all right, and that will, okay, force the task to actually hold on to the CPU and keep executing. All right, so I can just show you that over here. Okay, so I know we are nearing the end. So if you have to leave for another class, please go ahead and you can look at the video later. Okay, I just want to finish up these two questions here. All right. So let me just compile this and run. Okay, so this is not exactly 1 second. All right, but the idea is the same. So we are running a delay. So this delay function is this NOP delay function that we have been using all the while. All right, now if I run this, okay, you will see that in terms of LED behavior, it is still blinking. Okay, of course, it is blinking a bit faster now because it is not exactly 1 second. But what is more important is this is significantly different because this keeps this LED thread still in the run state throughout the entire time. Whereas the OS delay gives an opportunity for other tasks to run because you go to a block state. Okay, so that is the key difference here. Okay, so let me just change back this code. Okay, so let me go on to the next question here. All right, so this is interesting. Now we have two threads. Okay, previously it's only one thread, so easy to see. Now we have two threads, LED red thread, LED green thread. Okay, and the following code shows they are both doing the same thing. All right, so let me show you the code, okay, in full. So what I'm going to do here is I'm going to create two threads now. Okay, LED red thread and LED green thread, and both of them are exactly the same. Okay, so if you look at it, both of them are exactly the same. Okay, so of course, when I create two threads and both of them, the attributes are null. That means they both have the same priority. All right, then your what will happen? Okay, so I'm going to run the code, and what do you think will happen in this scenario when I run this code? Okay, so let me get your opinion first through a poll, and then we will see. Okay, that means I'm running this code. Okay, as what you saw just now, I will create both the threads, LED red thread, LED green thread. Okay, always remember at any point of time, only one task can run at a time, correct? Even though it's multitasking, only one task can run at a time. Okay, and as what we saw just now, when I call osDelay, I will make my task go to a block state. Okay, I'll make my task go to a block state. So what is the kind of LED behavior we would expect, okay, when I run this code? Okay, so quite close. About 43% say both LEDs on, both LEDs off together. And then 40% say red first, then green, and then you repeat red, green, and so on. Okay, so that is the general consensus. So it's either one of this. Okay, so let's see what happens. Okay, so let me run the code first. Okay, so let me just check. Okay, so both the threads are there and both of them are using osDelay. Okay, so let me rebuild the code. Okay, so now I run. So what do you see? You see it is yellow. Correct? You see it is yellow. Okay, why? Because red and green are coming together. Okay, so red and green together on, red and green together off. Okay, so why is that so? Because your LED, okay, uh, okay, would light up together because when we call osDelay, what happened? You will allow a context switch to happen, correct? Okay. So when you allow a context switch to happen, you will see that when the red LED is on, I will call osDelay, I'll do a context switch, and I'll immediately go to green LED to switch on. Okay, so let me show you a timing diagram and then you can see this better. So what is happening is I call red LED thread first. Okay, I'll transition to run and I'll switch on. All right, and once I switch on, the moment I call osDelay, I go to a block state. And when I go to a block state, the green LED thread, which was ready, right, which was waiting for a chance to run, will automatically run. All right, that means the moment I switch on the red LED, within a very short amount of time, I actually switch on the green LED. So it is actually, there is a time gap. Is only thing is it is so small that you can't see it. Right? Rightfully, there is a time gap because there is a time difference between after I switch on and then I call osDelay and I need to do a context switch. So there is some small amount of T here, but it's very, very small. Okay, so you don't see it as on red and on green or yellow. So what you see is both of them together, and then this 1 second also again they are both running concurrently, but since they are both called one after another very quickly, this 1 second also appears to be actually almost the same. But rightfully, the red thread comes out of the 1 second first, correct? So the 1 second finishes earlier for the red thread because you called it first. Okay, so rightfully what happens is when I come out of the osDelay, I will off the LED red first. Okay, so there will be a short period of time where only the green is on. Okay, where the green is on, and then When the OS delay finishes is 1 second, then the green goes off. Okay, but because it is so fast, okay, and the time difference is so small, you see it as being together. You see it as being together. Okay, so this is something you will observe in the lab. Okay, now just one more thing before we end. Just one more thing before we end. Uh, okay, so for this last part here, now, so this part I believe we can relate to what is happening because of the OS blocking call, and we are actually transitioning. Now, instead of doing the OS delay, okay, let's assume that right now I change everything to this delay. Okay, that means for both the LED red thread and LED green thread, instead of using OS delay, I use the normal delay. Okay, the normal delay, which is basically just a routine with a for loop or a while loop. Okay, so what do you think will happen now? Okay, so let me relaunch the poll. Okay, for this scenario, what do you think will happen? Okay, so I am not calling OS delay. So if I don't call OS delay, what do we know? We know that I will not go to a block state. Correct. So if I do not go to a block state, will I be able to transition to another thread? Okay, so I will end the poll now. Okay, because of time constraints, already almost 11:57 now. Okay, so about 53% say only red LED blinking. Okay, some say is red LED on and green LED on and repeat and so on. Okay, so only 1% said both LEDs on and off as before. Okay, so let's look at what is going to happen. So this is the code change. Let me save it. Let me rebuild the code. Okay, so we know that everything else is the same. Only thing is the LED call instead of using OS delay, I've used this delay. So let me run the code. Okay, so now if I run the code, let's see at the moment of truth. Okay, we see that it is still yellow. Okay, it is still yellow. That means for some reason, even though I am using a normal delay instead of OS delay, I am still transitioning between this thread and this thread. Right, that is the only way I can get yellow. That means both of them are on at the same time and both of them are off at the same time. All right, so this sort of suddenly contradicts what we just discussed. All right, it sort of contradicts what we just discussed. Okay, and why is this so? Okay, why is this so is something you will explore in the lab. All right, but just to give you a quick idea so that you do not lose sleep over it. All right, the reason is because if you look under RTX config, there is this thing called OS Robin timeout. All right, and this is something unique to the RTX RTOS behavior. That means threads that are within the same priority level will actually have a round robin behavior. Okay, so since both LED red and LED green are having the same priority and OS Robin is enabled, every 5 ticks, okay, will allow you to do a round robin switching. So that means I'll actually be continuously switching between the red LED thread and green LED thread, even though there is no call to block. So they are still running, but from running, they will actually switch to ready and run, okay, while they are switching going through this round robin because they are both of the same priority. So this is again a unique behavior that RTX RTOS has. Okay, and you will explore this in more detail in the lab itself. Okay, so yeah, I think that sort of gives you enough stuff for the tutorial. So tutorial basically you've covered everything. All right, and then this last part here is um, the lab. All right, yeah, okay, the demo for the for loop. Yeah, I forgot that. Okay, so let me just come back here. So what I want to show is this, correct? The for loop. If I remove this for loop here, which is in the main, what happened? Okay, so let me again rebuild the code. Okay, so what I've done is I have uh, removed the for loop over here. Okay, I removed the for loop over here. I commented it off. Okay, and the code is just now what we just ran, the two LED thread with a normal delay. Okay, so if I run, you'll see that there is actually no impact at all. The code runs as per normal. Okay, and why is that so? Because the moment you call OS kernel start, you will transition to the OS environment. All right, which means you actually do not come back to main at all. Okay, but why do they have this by default? Okay, the reason why they have it by default is sort of a safety check. That means if in any case your OS crashes and the system recovers back to single thread operation, you are still in that for loop and you're stuck there instead of the whole system just stuck in some unknown place. Correct. So by default, you have that for loop as a sort of safety catch, so that if the OS crashes, you still come back to the main. Okay, but by default, if everything goes well, all right, and your program is executing, once you call OS kernel start, you never come back to the main because the main is part of your single threaded environment. Once you call OS kernel start, you are permanently switching over to the multi-threaded environment. Okay, so I hope that clears up everything. Okay, sorry for taking so much of time today. I just wanted to make sure that all these basic concepts are clear. All right, because this is very important to make sure that when you are going to learn all the other OS stuff, these fundamentals are strong. All right. Okay, so that should give you enough to cover the lab for this week. All right, so next week we will look at more OS concepts and more important aspects of how we can design multi-threaded code that can help you with your project. Okay, so again, thank you very much. Okay, I will see you all next week.